Alright, so this is the second video, part B, for the 5.4 notes. So we left off, we're ready to start objective 3, which are identifying domains of the trigonometric function. Right? So it's just some things to think about. If we, first just start with sine. So if we have sine of t, remember we looked at before, that's just equal to y, right? When we're, defining the trigonometric function on the unit circle, right? Also, cosine of t is equal to x, right? So when thinking about both of these, there's going to be no restrictions on the domain, right? Because we're just getting some value back, right? There's nothing in the denominator, right? But when I have, let's say like tangent of t, which is equal to y over x, we can't have x being equal to 0, right? And the other trig function that has x in the denominator is secant of t, which is equal to 1 over x, right? So in both of these cases, we cannot have x being equal to 0, right? So let's think about, when is x equal to 0, right? So if I go back up here to my diagram of the unit circle, let's see, I got written all over. I think I have another one here that's cleaner. When is the x coordinate equal to 0? Well, that's going to be at this point here and this point here, right? So this is, at pi over 2, and this is at 3 pi over 2, right? But then, I could go around again, and, this would be, 5 pi over 2, and then this would be 7 pi over 2. Right, so essentially, we just keep adding 2 pi, right? Because 5 pi over 2 is equal to pi over 2 plus 2 pi. So in other words, we went around one time and then landed back here again, right? So we had one full rotation and then another pi over 2 rotation. And then this guy, is 3 pi over 2 plus 2 pi. Right? So we could keep doing this, right? And still landing at those same spots, right? So essentially what I'm trying to show, right? So we could say that x equals 0 when t is equal to pi over 2 and when t equals 3 pi over 2. Right? So in other words, t cannot be equal to, because we don't want it to be equal to 0, cannot be equal to pi over 2, 3 pi over 2. And then we keep going around rotations, right? So we had 5 pi over 2 and 7 pi over 2. So this guy was pi over 2 plus 2 pi. And this guy, 7 pi over 2, was 3 pi over 2 plus 2 pi. Right, and then we could keep going, right? Keep adding 2 pi to each of these. It turns out that these have a pattern. These are just odd multiples of pi over 2. Right? Notice my odd integers, 1, 3, 5, 7, 9, 11, so forth. We're just taking those numbers and multiplying by pi over 2, right? So if we compare these two sets, right? So the first one would be 1 times pi over 2 and then 3 times pi over 2, right? So if that doesn't make sense, I can write this out. So this would be like 1 times pi over 2. This guy would be 3 times pi over 2. This would be the same thing as 5 times pi over 2, 7 times pi over 2, and so forth, right? So we're just taking these odd multiples of pi over 2. Right, so something you may have seen before. How do we come up with an odd number in guarantee we have an odd number in mathematics? Well, if we let n be an integer, if you forget what an integer is, it's in this set. Another way to write this same thing is n epsilon, and then the symbol for integers was a boldface z, right? That would mean the same thing, right? We're just saying n be an integer. Well, if I take 2 times n, what this guarantees is I have an even number, right? So twice any integer is going to be an even number, right? That's what an even number is, a number that's divisible by 2, right? So then if we think about how the number line works, it keeps going even, odd, right? So we would have, like 0, 1, 2, 3, 4, 5, 6, and so forth. Think about, with the whole numbers, we're going even, odd, even, odd, even, odd, even, odd, so forth, right? That's going to continue, right? So what we can say is that 2n plus 1 is going to guarantee it's going to be an odd number, right? So that's what we're after, right? So how can I show an odd multiple of pi over 2? So I can conclude, I can say, so t cannot equal pi over 2 times 2n plus 1, right? And if we wanted to, we could take pi over 2 times 2n plus 1. We could distribute the pi over 2 through. So that would be 2n times pi over 2 plus pi over 2, which is equal to, so the 2's here would cancel, so we get n pi plus pi over 2. Right? So in other words, we can say that t cannot be equal to n pi plus pi over 2. Right? So that's just another way to write that. All right, so running out of room here, so I'm just going to come off to the side and finish up the next part of this. Is we wanted to think about when y is in the denominator, right? So that would be with cotangent of t, which is equal to x over y, and also cosecant of t, which is 1 over y, right? So in both of these cases, y cannot be equal to 0, right? So again, if we go back to our unit circle here, so it's just, oops, let me scroll down. Let me erase this. Right, so y is going to be equal to 0 at these 2 points, right? So this is at 0 and 2 pi, right? This would be at pi and 3 pi, right? If I going around, adding a rotation in. So, adding one rotation, this would be 4 pi, and this would be 5 pi, right? And we would, could keep going, adding more and more rotations in, right? So essentially, what we have is that, y is equal to 0 when t is equal to 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, and so forth, right? So notice what we get is that these are just multiples of pi, right? So in other words, we would say that t cannot be equal to n pi for some integer n. Remember, I could show that as n is within the integers, right? We could just say that instead of this part. Right, so I could do the part circled in green or this part boxed off in green, right? Either one. Right? So then the next part that we want to write here is filling in, reminding us what's the domain of a function, right? So I don't have room left there, so I'll just write it here. So the domain is the set of all possible inputs for the function. Right? So you should remember that from college algebra, right? So if we think about the domain for each of the trig functions, the exercise we just went through will help us do this, right? So remember, for sine and cosine, we said that there were no restrictions, right? Anything would work, right? So we could just say the domain for sine is all real numbers. Right? So there's a couple of ways to write that. You could do it with the set symbol for all real numbers, which is a boldface R like that. Or you could write this in interval notation, which would be negative infinity to infinity. Right? Either one of those would be fine. And for the notes column, we could just say that there's no restrictions. Right? So then for cosine, same thing really, right? Same domain. We would say that there's no restrictions. So all real numbers. Right, we could show that again with a boldface R or an interval notation. Right. So then remember, tangent and secant matched, right? So these two guys matched. So if you remember, what we needed to exclude were odd multiples of pi over 2, right? So we need to exclude odd multiples of pi over 2, which I'll just put in parentheses, just a reminder that's 90 degrees, right? So that would be the same for secant, right? We need to exclude odd multiples of pi over 2, which is 90 degrees. Right, so to be able to write the domain, I'm going to write this in set builder notation, right? So, we start with a set symbol. What my thing looks like is a T, then we draw a horizontal line, or excuse me, a vertical line, and that, basically we're saying the set of all T such that, and then to the right of the side are the condition. So the condition is that T cannot be equal to 2n plus 1 times pi over 2 for integer z, or integer n. Right, so that's set builder notation, right? So I believe you should have went over that in college algebra. If you don't know set builder notation, feel free to drop in my office hour, and I'll be glad to help, or send me an email. So then secant, right, would just be the exact same thing, right? So it would be the set of all T such that T cannot be equal to 2n plus 1 times pi over 2 for integer n, right? So since these are kind of close together, let me change color here. So remember, cotangent and cosecant were similar, right? They were the same. So remember, with these, we said that we need to exclude multiples of pi, which is 180 degrees. Right, so how we can write that in set builder notation. So we'd have the set of all T such that T is not equal to n pi for some integer n. Right? So same thing, a set of all t such that t cannot equal n times pi for n for some integer n. Right? So just notice here I have a statement here that, so we're only focusing in on the domain right now, but in sections 5.5 and 5.6 we're going to cover the graphs of these functions, and we'll focus in on the ranges at that point, right? All right, so the next page, let's see, let me erase some things here that I had written on this. So this is just at the top of the page, just a filled in version of the unit circle. And if you just Google unit circle, you might be able to find some good diagrams, right? But there's just one there to have as a reference. So now we're ready to look at some examples. Example 3 has 2 parts. We're asked to evaluate the function or state the function is undefined at the given value, right? So the very first thing, I'm looking at cotangent of pi over 2. So remember that cotangent of pi over 2 is equal to x over y, right? So looking at the unit circle, pi over 2 is at this point, right? So in other words, we could write that pi over 2 corresponds to the point 0, 1 on the unit circle. Right? So the x value is 0, the y value is 1, so 0 divided by 1 is just 0. Right? So cotangent of pi over 2 gives me 0. Right? And then next we're looking at cosecant of negative 2 pi. Right? So negative 2 pi would be going, in this direction. Let me switch colors. Right? Starting here, the negative direction, but we're going this way. Right, we would do one full rotation, so we're going to end up landing back on the same point, right, of 1, 0. So negative 2 pi corresponds to the point 1, 0 on the unit circle. So cosecant of negative 2 pi is equal to 1 divided by y, which would be equal to, so we'd have 1 in the numerator still, but my y coordinate is 0, right? We can't divide by 0, so this is equal to undefined, right? So cosecant of negative 2 pi is undefined. So remember with cosecant, the domain was excluded if we had multiples of pi, which negative 2 pi is a multiple of pi. Right? All right, so now we're ready to look at the last objective in the section, objective 4. So what we want to be able to do is apply the period and properties of trigonometric functions. Right? So first, I just have a definition of what a periodic function is, right? So a function f is periodic if f of t plus p is equal to f of t for some constant p. The smallest positive value for p for which f is periodic is called the period of f, right? So essentially, if I can add some constant p to the input and I get the same output as if I didn't have that p there, then that means it's periodic, right? Like repeats itself, right? So it turns out that the period of sine, cosine, cosecant, and secant are all 2 pi, right? So these are all 2 pi, or we could say 360 degrees. So 2 pi or 360 right? And it turns out that tangent and cotangent have a different period than the others. Their period is actually pi, or 180 degrees. Right? So then what we could fill in by thinking about this periodic thing, right, is if I have sine and I take t plus the period 2 pi, this is just going to be equal to sine of t, right? So we could also write this using degrees, and I'll use theta instead of t. So we could say, sine of theta plus 360 degrees is equal to sine theta. Right, so that's just using that definition of periodic, right? We know what the period is, so this is what we can conclude, right? So then for cosine, we could say, cosine of t plus 2 pi is equal to cosine of t. We could say sine of theta plus, we'd want cosine here. Cosine of theta plus 360 degrees is equal to cosine of theta, right? So all we're doing now is just essentially substituting in the different trig functions, right? Because they all have the same period. So cosecant of t plus 2 pi is just equal to cosecant of t, and cosecant of theta plus 360 degrees is also equal to cosecant of theta. And then we would have, secant of t plus 2 pi is equal to secant of t, and secant of theta plus 360 degrees is equal to secant of theta, right? So then, switching it up here for tangent, the difference is we would have, tangent of t plus pi equals tangent of t, and tangent of theta plus 180 degrees is equal to tangent of theta. Then cotangent of t plus pi is equal to cotangent of t, and cotangent of theta plus 180 degrees is just equal to cotangent of theta. Right, so these properties will come in handy, right, knowing the period. All right, so example 4 has 3 parts, and we're asked to use the unit circle and the period of the function to evaluate the expression if possible, right? So we're trying to find cosine of negative 7 pi over 3. Well, this would just be equal to cosine of negative 7 pi over 3 plus 2 pi, right? Because the period is 2 pi. And I'm trying to get this to be, on the unit circle, so within one rotation. So that, this would become cosine of negative 7 pi over 3 plus, and I could rewrite 2 pi with a denominator of 3. So multiply top and bottom by 3, we get 6 pi over 3. So then negative 7 pi over 3 plus 6 pi over 3 gives me cosine of negative pi over 3. So we're still not within a full rotation. So I can add 2 pi again. So we get cosine negative pi over 3 plus 6 pi over 3, which equals cosine of 5 pi over 3. Right, so then I can look at my unit circle. So So 5 pi over 3, excuse me, is, where is it? It's here. Right, so cosine is the x-coordinate, so we just want that x-coordinate, which is a half, right? So this is equal to 1/2. Right, so then tangent of 600 degrees would be equal to tangent of 600 degrees. And I'm going to subtract 360 degrees. Right, that's still a multiple of the period, right? It's just the -1 times the period, which is, well, actually, I'm doing it twice, right? So if you wanted to write it out, we would write 180 degrees, remove one period, which will give me tangent of what, 420 degrees, and then I could subtract off. So this would be the same thing as tangent of 420 degrees minus 180 degrees, which is equal to tangent of 240 degrees. So remember, this is y over x, right? So here we put the y coordinate, here we put the x coordinate. So if we look at the unit circle, we're focusing in on, let's see, 240 degrees, which is here. Right, so you can see the x coordinate is -1/2 and the y coordinate is negative radical 3/2. So just filling those into the appropriate spot, we'd have negative radical 3/2 all over -1/2. And we could make this a little simpler. I can multiply top and bottom by -2/2. So what this will give me would be a radical 3/1, which is just radical 3. Right. So then cosecant of 5 pi, right? So for cosecant, the period is 2 pi. So this would be equal to cosecant of 5 pi minus 2 pi, which is equal to cosecant of 3 pi. So I need to remove 2 pi again. So this would be equal to cosecant of 3 pi minus 2 pi, which is equal to cosecant of pi. Right? So cosecant would be what? Lost my train of thought. Hang on. Cosecant. Right, so cosecant is 1 over y, right? So we can just fill in the y coordinate here. So first let's find pi. So I'll do this in orange, so we'd be focusing on here, right? So the point that we're looking at is -1, 0. We want the y coordinate, which is 0. So we would end up having 1 divided by 0, which is undefined, right? Because we can't divide by 0. Right? All right, so what I want to do next is just briefly review even odd functions, and for the discussion board post, you'll need to know the even and odd functions for this week, and I posted some resources in the assignment to also help you with this. So I'll just review it real quickly here for our purposes, and then you can look at that in more depth if you forget what even and odd functions are from college algebra. So even functions, and we want to look at odd functions. So remember, a function is even if f of negative x is equal to f of x for all x in the domain. Right? A function is odd if f of negative x is equal to negative f of x for all x in the domain. Right? So an even function is symmetrical with respect to the y-axis. Right? Also, just another note is that if the point xy is on the graph, then the point negative x comma y is also on the graph. Right? And then a basic example, when I think about like the most basic even function, is just f of x equals x squared. Right? So, just a quick sketch, we have a graph that looks like this. Right? So when we look at an odd function, a note for an odd function is that odd functions are symmetrical with respect to the origin. Another note is if the point xy is on the graph, then the point negative x comma negative y is also on the graph. And then, the most basic odd function that I think of is f of x equals x cubed. Right, so a quick sketch of the graph of that looks something like this. Right, well, here's x and y, x, y. Right, so it's just a quick review. So we can think about even and odd properties of trigonometric functions. Right, so if we evaluate, sine, cosine of the trig functions at t and also negative t, then we can think about the property. So it turns out that sine of t is going to be equal to y, and if I take sine of negative t, this equals negative y. Right? So the property that we could say is that negative y would be equal to negative sine t, right? So if I multiply both sides in the top, if I multiply this times negative 1 and this times negative 1, that gives me that negative y equals negative sine t, right, is what I'm after. So the property that we could say is that sine of negative t is equal to negative sine t, which means that it's an odd function. Right? And then if we look at cosine of t, is equal to x. It turns out that cosine of negative t is also equal to x. So what that means is that cosine of negative t is equal to cosine of t. So from our definition of even odd functions, that means this would be an even function. Right? So cosecant of t is equal to 1 over y. It turns out that cosecant of negative t is equal to negative 1 over y, right? Which would be equal to negative cosecant of t, right? Same rationale as up here with sine, right? So in other words, cosecant of negative t is equal to negative cosecant of t. So that means that this is an odd function, right? So then secant, secant of t is equal to 1 over x, right? So secant of negative t turns out to be equal still to 1 over x, right? So in other words, secant of negative t is the same as secant t. So this is an even function. Right. And then we'll look at the next two, which are going to be odd, right? So an easy way to remember it is that cosine is even, and its reciprocal function, secant, is also even, and the rest of the functions turn out to be odd. So tangent of t is y over x. It turns out that tangent of negative t is equal to negative y over x. So what that means is that tangent of negative t is equal to negative tangent of t. Excuse me. Right, because again, we can multiply both sides by -1, and that's where I get that from, right? So that means that this is an odd function, right? And then cotangent of t is equal to x over y. And it turns out that cotangent of negative t is equal to x over negative y. So cotangent of negative t then would be equal to negative cotangent of t, which means this is an odd function, right, as promised, right? So these are my two even functions. The rest are odd. Right, once we look at the graphs too, I think it'll make it a little easier to remember that when we think about the graph of cosine versus sine, and we'll look at that in the coming sections. All right, so we have two examples left to get through. So practicing with example 5, we're practicing using these properties of the trig functions we just looked at to try to simplify the given expression, right? So so the first one we have secant of theta minus 2 secant of negative theta. So there's not a lot I can do here with secant theta, right? It's just an expression. But since we have secant of negative theta, it'd be really nice if I could rewrite this using the even-odd idea, so that way I could just have everything in terms of secant theta. They'd be like similar terms, right? So if you remember up here, right, secant is an even function, so secant of negative t is just equal to t, right? So in other words, here, secant of negative theta is just going to be equal to secant theta, right? Because secant's even. So this would be equal to secant theta minus 2 times secant theta. So now that I have like terms, I can just simplify, right? Because this is like 1 secant theta. So 1 secant theta minus 2 secant theta would just be negative 1 secant theta. Right, so we're able to simplify that. The next one, we have sine of 2t plus 2 pi minus sine of negative 2t. Right, so we can use a couple of these properties. So the first one, the first term here, we're adding 2 pi to the degree. So that's 1 period, right? So this sine of 2t plus 2 pi would just be equivalent to sine of 2t, right? Because I don't need that added period in there. So then we'd have, minus sine of negative 2t. And then next, I want to deal with this negative sign, right? So remember that sine is an odd function, right? So in other words, sine of negative 2t is going to be equal to a negative sine of 2t, right? So what this would give me is sine of 2t minus, and then this would be filled in with negative sine of 2t. So these two negatives, right, would make addition, so this would be sine of 2t plus sine of 2t, which would be equal to, there's two of them now, right, 2 times sine of 2t, right? So that would be as simplified as we can go using those properties. So then the last one I have here, example 6, so it says for given real number t, express tangent of t in terms of secant. So the hint is to begin with x squared plus y squared equals 1 and divide both sides by x squared, right? So, thinking through this, right, just to remember some things, is that tangent of t is equal to y over x. Secant of t is equal to 1 over x, right? So if I have, the expression x squared plus y squared equals 1, notice that both of these have x in the denominator, right? So that's why it makes sense to, well, let's divide both sides by x squared, right? So if I divide both sides by x squared, right, you might be thinking, why aren't we dividing just by x? Why are we dividing by x squared, right? Well, it's it's because, this is y squared, right? That's the main thing. And also this x squared. If I were just to divide by x, it wouldn't be so helpful, right? But you'll see here in a moment, since I'm dividing both sides by x squared, this will turn out to be a lot nicer. Right, so let me just write this out. Right, so we get x squared over x squared plus y squared over x squared equals 1 over x squared. So x squared over x squared is just 1. So we'd have 1 plus, and then we'd have, this should be x squared. Then we'd have y squared over x squared equals 1 over x squared. Right. So now let's think about these with some exponent rules. So x squared over x squared, y squared over x squared is the same thing as y over x quantity squared, right? It's using the exponent rule. If I have a over b to the nth power, this is equal to a to the n over b to the n, right? So it's kind of like in reverse. We're essentially going in this direction, right, with this rule here, right? So since we have the same exponent, we have a base to an exponent divided by a different base of the exponent, same exponent. That's why we can rewrite it in that fashion. And then also dealing with 1 over x squared, I can think about this as 1 squared over x squared, right? So using the same idea, this would be 1 over x quantity squared, right? So we can substitute those values in, and what we get is 1 plus y over x quantity squared equals 1 over x quantity squared, right? And the reason why I wanted that, right, because I'm trying to get this in terms of tangent and secant. Well, secant's 1 over x and tangent's y over x. So now I have those, right? Because, here's y over x, here's 1 over x, right? So this would give me 1 plus, so if I just fill this in, that would be tangent of t squared equals, this would be secant of t quantity squared. So remember how we write that is 1 plus tan squared t equals secant squared t. That's how we write that. And then we're trying to express tangent in terms of secant. So in other words, we want to solve for tangent. So I want to subtract 1 from both sides. I get tan squared t equals secant squared t minus 1. And then we don't want tangent squared by itself. We want tangent by itself. So what I can do is take the square root of both sides. And when I do that, I need to put a plus or minus on one of the sides, right? So then what we get is that tangent of t is equal to plus minus the square root of secant squared t minus 1. Right? All right, so that's the rest of this notes. If you have questions, make sure you let me know. I'll be glad to help.